identical balls, each having a density rho, are suspended from a common point. This is a common point. These are the two balls are suspended through a common point by two insulating strings of equal length. Both the balls have same mass and charge. In equilibrium, each string makes an angle theta with the vertical. Now, both the balls are immersed in a liquid. As a result, the theta angle does not change. Density of the liquid is sigma. Dielectric constant of the liquid will be. So, because of the dielectric constant, the force between the charges is going to get affected, and due to the liquid, one more thing is going to come into picture is the buoyant force. So, first of all, let us consider the first situation in which these two balls are repelled away from each other due to this electrostatic force. Here, this is electrostatic force F, and the medium at this time is normal air. Okay, suppose T is the tension in the rope. So we can find two components of the tension along the horizontal and vertical. Okay, theta is the angle made by the string with the vertical. So this particular angle is also going to be theta. So vertical component of the tension is T cos theta, and the horizontal component is T sin theta, and F is the electric force, and this one is weight of the object. So what is the weight? Since density is given, and suppose V is the volume of this ball, then V volume into rho density becomes mass into G will be the weight. Since this object is in equilibrium under these forces, so these forces must be balanced. So we can write along the vertical direction, the equation will be T cos theta is equal to V rho G. For the vertical direction, T cos theta must be equal to the mg, the weight of the body. And the horizontal component of the tension must take care of the electric force. So it is T sin theta is equal to F. Okay. So using these two, at least at this time, we can find the value of the tan theta, which is going to remain same in the second situation. If we divide second equation by the first one, so we get the value of the tan theta as F divided by V rho G. Now let's move to the next situation when this whole setup is immersed in a liquid of density rho. Then what happens? It is given that as a result, angle theta does not change. That means in both the cases, angle theta is going to remain the same. So this angle remains theta. Okay. So here T is the tension, and this is V into rho into G, which is weight of the object. And this is electric force, which was F in previous case, but this time it is going to be F divided by K, because K is the dielectric constant of this medium in which the whole system is immersed. Alright, so component of T in the vertical upward direction is going to be T cos theta, and in the horizontal direction it is going to be T sin theta. In addition to these forces, there is additional force, which is the buoyant force B. So what is the buoyant force? Buoyant force will be the volume of the object multiplied by the density of the liquid, which is given to be the sigma into G. So it will be the buoyant force. So under the action of these forces, the object is in equilibrium. Both the objects, the situation is symmetric for both the objects. So same force diagram will be there for another one. The same is here also. So for vertical equilibrium, as you can see that T cos theta plus buoyant force, which is V sigma G, is going to balance the weight, which is V rho G. And this time tension is going to change. So it's better if we assume some other symbol. Let us to be T dash, okay, because in both cases tension will be different because the forces are changing. So T dash cos theta plus V sigma G is equal to V rho G, which is weight. So this way we get T dash cos theta this time equal to V into rho minus sigma into G. Okay. And in case of for horizontal equilibrium, we have T dash sin theta equal to F electric. F electric is F by K now. As we know that in case of vacuum, force between two particles is 1 upon 4 pi epsilon naught Q1 Q2 divided by R square, and in case there is some medium, then the same force becomes, let us it to be F naught, and in case of medium, the same force becomes 1 upon 4 pi epsilon naught into K into Q1 Q2 divided by R square, where K is dielectric constant of the medium. So here I am not writing the detail of the force because that's not required here. So T dash sine theta is equal to F by K. So we can divide these two equations to get the value of the tan theta this way. So tan theta will be, by dividing second equation with the first one, we get tan theta equal to F divided by K into V into rho minus sigma into G. So this is the value of the tan theta. But we have calculated the value of the tan theta earlier also. So we can equate that value. So here you can put the value of the tan theta, the earlier one, because this is the key point of the question, that in both the situations the value of the theta remains same. So by equating these two, you can clearly see that V and V are cancelled, F and F are cancelled, G and G are cancelled. So K that we get here is what? Rho divided by rho minus sigma. Okay, so this is the dielectric constant of the medium, and because of this dielectric constant, the angle the string makes with the vertical is not changing. Option B obviously is the correct choice.